If 120 volts direct current of 5 amps is applied to a 120 volt alternating current at 5 amp contactor, the contactor would likely be damaged or destroyed. Alternating current contactors are designed to handle the alternating polarity of alternating current, while direct current contactors are not. The sudden change in polarity would cause arcing and overheating, leading to failure. If 120 volts alternating current at 5 amps is applied to a direct current contactor, the contactor would not operate properly. Direct current contactors require a continuous flow of current to hold the contacts closed. Alternating current periodically reverses polarity, causing the contacts to open and close rapidly, preventing the contactor from performing its intended function. In more detail, let's examine why this happens. Firstly, alternating current contactors are typically designed with laminated cores. These cores are made up of thin sheets of metal insulated from each other. This lamination is crucial for reducing eddy current losses, which are significant in alternating current circuits due to the constantly changing magnetic field. When direct current is applied to an alternating current contactor, the laminated core becomes a problem. The direct current creates a constant magnetic field, which saturates the core. This saturation prevents the contactor from properly opening and closing, and it also leads to excessive heat buildup. The heat is a result of increased current flow in the coil, as the impedance of the coil is significantly reduced with direct current compared to alternating current. Secondly, the coil insulation in alternating current contactors is often not designed to withstand the constant voltage stress imposed by direct current. Alternating current voltage changes direction periodically, so the insulation experiences brief periods of peak voltage followed by periods of lower voltage. Direct current voltage, on the other hand, applies a constant voltage stress which can degrade the insulation over time, leading to insulation failure and short circuits. Thirdly, the contact materials used in alternating current contactors are typically optimized for alternating current applications. These materials are chosen for their ability to withstand the arc that forms when the contacts open and close under alternating current conditions. Direct current arcs are generally hotter and more sustained than alternating current arcs, which can cause the contact materials to melt, pit, and erode more quickly. This damage reduces the contactor's lifespan and its ability to carry current effectively. Fourthly, the operating mechanism of an alternating current contactor is often different from that of a direct current contactor. Alternating current contactors typically use a shading coil to ensure that the contacts remain closed during the brief periods when the alternating current voltage crosses zero. This shading coil creates a phase shift in the magnetic field, which keeps the armature pulled in. When direct current is applied, the shading coil becomes ineffective, and the armature may chatter or vibrate, causing noise and premature wear. Now let's consider what happens when alternating current is applied to a direct current contactor. Firstly, direct current contactors are designed with solid cores, not laminated cores. These solid cores are suitable for direct current applications because there are no eddy current losses with a constant magnetic field. However, when alternating current is applied, the solid core becomes a major source of eddy current losses, which can cause the core to overheat rapidly. This overheating can damage the coil insulation and other components of the contactor. Secondly, the coil impedance of a direct current contactor is much lower than that of an alternating current contactor. This is because the coil is designed to operate with a constant direct current voltage, which means it has fewer turns of wire and lower inductance. When alternating current is applied, the low impedance causes a very high current to flow through the coil, which can quickly burn out the coil. Thirdly, the contacts in a direct current contactor are typically designed to handle the sustained arc that forms when the contacts open under direct current conditions. These contacts may be made of different materials or have a different shape than the contacts in an alternating current contactor. When alternating current is applied, the contacts may not be able to handle the alternating current arc effectively, leading to contact damage and failure. Fourthly, the operating mechanism of a direct current contactor is designed to provide a strong and consistent force to hold the contacts closed. This is necessary because direct current circuits often involve inductive loads, which can create significant back electromotive force when the circuit is interrupted. When alternating current is applied, the operating mechanism may not be able to respond quickly enough to the rapidly changing voltage, causing the contacts to chatter or bounce. This chattering can create additional arcs and accelerate contact wear. In summary, using direct current on an alternating current contactor or alternating current on a direct current contactor can lead to a variety of problems, including overheating, insulation failure, contact damage, and operational malfunction. It is essential to use the correct type of contactor for the intended application to ensure safe and reliable operation. Furthermore, understanding the design differences between alternating current and direct current contactors is crucial for troubleshooting electrical systems and preventing equipment damage. When selecting a contactor, always refer to the manufacturer's specifications and application guidelines to ensure compatibility with the voltage, current, and type of load being controlled. Proper selection and installation of contactors are essential for maintaining the safety and reliability of electrical systems.